All right, guys, here we go. We're going to start with a video. We're going to start with a video. You ready?
Hello, and welcome to a video about hybrid orbitals, often called valence bond theory. Developed in the 1930s by the great chemist Linus Pauling as a model of bonding to understand the three-dimensional placement of atoms in a molecule, and that is critical to our understanding of the properties that molecules have.
Both my kids are happy, eager little learners. Since Audrey has started with White Hat Junior, her grades
My students too.
so much.
In this video, we will look at methane, ethene, ethine, ammonia, and water as our models for hybridization. There is only a small group of atoms in the second period that the model really works for, but among those are carbon, nitrogen, and oxygen, which make up the vast majority of molecules that exist on Earth. So the model applies to a limited number of elements, but it applies by far to the majority of molecules. Let's take a look at the word hybrid. It is a blending of two varieties. If you get a horse and donkey together, you get a mule, a blending or hybrid of a horse and a donkey. Let's get to hybrid orbital, using carbon as our model. As a single atom, not bonded to anything, carbon has 2 electrons in 1s, 2 electrons in 2s, and 2 electrons in 2p. This electron configuration is the energy arrangement of carbon's electrons. However, carbon rarely exists in nature as an individual atom, except momentarily while undergoing chemical reactions. Carbon exists with its valence electrons bonded to other atoms. When carbon bonds to 4 other atoms, carbon's 4 bonds are experimentally seen to be equivalent. And so when the carbon atom finds itself in a bonding situation, its bonding electrons themselves exist at equivalent energies, which requires that they hybridize to an energy that is intermediate between the 2s energy and the 2p energy. Or you can think of it as a blending or hybridization of the two energies, the s and p energies. And since the energies of these electrons have now changed, the shape of the orbitals they occupy are different as well, which we will see momentarily, and those are called hybrid orbitals. They are named 2sp3 hybrid orbitals. The naming often trips up students, so before we go any further, let's take a look at where the 2sp3 name comes from. The 2 comes from the second principal energy level that the valence orbitals are in. The s comes from the 2s orbital contributing to the hybridization, and the p comes from the 2p orbitals contributing to the hybridization, and the 3 comes from the number of 2p orbitals used in the hybridization. Once hybridized, the 2s and 2p orbitals no longer exist, and so we have 4 2sp3 hybrid orbitals. 4 2sp3 hybrid orbitals derived from combining the energies of 1 2s orbital and 3 2p orbitals, which gives a total of 4 2sp3 orbitals. Before we look at the shape of hybrid orbitals, it would be helpful to briefly review the atomic orbitals. The 1s orbital is a sphere, the 2s orbital is a larger sphere surrounding 1s. And here we will get rid of 1s since we are only concerned with the valence electrons. Each 2s orbital is a 2-lobed shape converging at the nucleus. So there are the 3 2p orbitals. However, when hybridization occurs, the s and p orbitals cease to exist, and the 2sp3 orbitals have an entirely different shape. We can see that orbital hybridization explains the VSEPR placement of carbon's 4 valence electrons. Since all 4 2sp3 orbitals are equivalent, each 2sp3 orbital repels the others with equal force, resulting in identical bond angles. The carbon atom only hybridizes when it is in a bonding situation. Here, 4 hydrogen atoms bond to carbon by overlapping their orbitals with carbon's hybrid orbitals. So what would be the reason for this? If we go back and see that both carbon and hydrogen have unpaired electrons, the overlap allows the electrons to pair and thus go to a lower potential energy. The illustration here contains the valence electrons of both carbon and hydrogen. And since everyone likes to visualize atoms as spheres, we can do the same. Here is our carbon atom, and here are the hydrogens with the overlapping spheres, indicating the overlapping orbitals that constitute the bond. The bonds are more readily discernible in a ball and stick model, which also makes the bond angle more visible. Since all 4 sp3 orbitals are equivalent, each bonding orbital repels the others with equal force, resulting in identical bond angles. The bonds in hybridization also have their own nomenclature. The overlapping orbitals are called sigma bonds, which represents the single bond occupied by a single pair of electrons. What about double bonds? How does the hybridization model explain double bonds? We will use ethane, C2H4, to see what happens in a double bond. The single bonds we know are sigma bonds, and the double bond also has a sigma bond, but the second bond of a double bond is a pi bond. Let's see how hybridization and orbital overlap can explain a double bond. The 2 carbon atoms in ethane are equivalent, so let's look at one of the carbon atoms first. A pi bond comes from the overlap of unhybridized p orbitals, and so the atom hybridizes only 3 orbitals, leaving a p orbital unhybridized for the pi bond. The hybrid orbital is called 2sp2, the superscript 2 denoting that only 2 2p orbitals have contributed to the hybridization. The 2sp2 hybrid orbitals exist in a plane perpendicular to the unhybridized 2p orbital. Let's remove the 2p orbital for now to more easily see that. The 2p hybrid orbitals are spread out at a 120-degree angle, which means that they exist in a plane, and the plane is perpendicular to the unhybridized 2p orbital. So this is what both carbon atoms do when bonding occurs in ethane. Each carbon atom is sp2 hybridized. The sigma bond occurs with 2sp2 orbital overlap. What about the pi bond, the second bond of the double bond? Previously we said that it comes from the unhybridized p orbitals, which we see here from both carbon atoms. The top and bottom lobes of the 2p orbitals overlap above and below the axis of the sigma bond, forming a single pi bond, the space in which the now paired electrons move around. The ball and stick model shows this double bond with 2 dashes. To summarize, sigma bonds occur along the axis between nuclei. The pi bond occurs above and below the sigma axis, where the p orbital lobes have overlapped. The ethane molecule also bonds to 4 hydrogen atoms by overlapping with both carbon's other 2 sp2 hybrid orbitals, creating 4 more sigma bonds. In the ball and stick model, we can readily see that each carbon has a trigonal planar geometry, and thus the whole molecule exists in a plane with the single pi bond above and below that plane. Now let's look at how hybridization can be a model for the triple bond using ethyne, C2H2. The carbon-hydrogen bonds are sigma bonds, and the triple bond is 1 sigma bond and 2 pi bonds. Let's see how hybridization can accommodate this. Since pi bonds come from p orbitals, and we need 2 pi bonds, then 2 2p orbitals have to remain unhybridized, and so the remaining single 2s orbital and a single 2p orbital will hybridize to 2 2sp hybrid orbitals. And there is also the violet 2px and the blue 2py orbitals. Here, each green lobe is a single orbital, and so they each have an electron, while both violet lobes constitute the single 2px orbital with a single electron, and both blue lobes constitute the single 2py orbital with a single electron. The other carbon in C2H2 also has that same triple bond, and so it has the same hybridization. Let's see what happens during bonding. sp orbitals from both carbons overlap, forming a sigma bond. The upper lobes of the blue 2p orbitals overlap, as do the lower 2 lobes, creating the first of the two pi bonds. Can you guess where the second of the two pi bonds comes from? Yes, that's right. It is the overlapping of the violet 2p lobes. Let's get rid of the sigma bond for a moment to take a look at something interesting. Each pi bond lies on a separate plane, and the two planes are perpendicular to each other, and so the two pi bonds are perpendicular to each other. Finally, two hydrogens will overlap with the remaining sp hybrid orbitals, creating the C2H2 molecule. The overlap of the space-filling model reflects the overlapping orbitals, which is also represented by the ball and stick model. In the remainder of the video, we will look at hybridization of nitrogen and oxygen using NH3, ammonia, as our model for nitrogen hybridization, and H2O, water, for our oxygen model. In NH3, nitrogen has 3 sigma bonds and a lone pair. So how does hybridization account for this? The hybridization is 2sp3, and nitrogen has 5 valence electrons, so one of the 4 2sp3 hybrid orbitals has a pair of electrons. The 3 sigma bonds come from the sp3 orbitals with a single electron, so they can pair up. And so the remaining electron pair is a lone pair, an unbonded pair of electrons. As with sp3 hybridization in carbon, nitrogen's hybrid orbitals spread out in a tetrahedral shape. And lastly, water. Here, oxygen has 2 sigma bonds and 2 lone pairs. In water, oxygen is also 2sp3 hybridized, but with 6 valence electrons. 2 of the sp3 orbitals have paired electrons. You can probably guess that the sp3 orbitals with a single electron will overlap with hydrogen. And the remaining 2 pairs are unbonded. They are lone pairs. Again, oxygen's hybrid orbitals spread out in a tetrahedral shape. That's it for hybridization, the product of a mad scientist. See ya.
Okay, that last part was really corny, but what did you think?
I think you had a really boring voice.
I feel like I need you to talk me through it. They gave a good, ground, basis of it, but it's just, he went really fast.
Used a lot of letters.
Okay. So, I'm sure you can already guess. VSEPR theory does a great job, except it has some limitations. Experimental data shows that the bonds are the same in some of the molecules. The bonds are the same, even though VSEPR would predict that they're not, that they're slightly different. So that's one of the limitations. Another limitation is that transition metals form these complexes, and just like the name says, they're complex. And VSEPR does not predict the proper geometries for those metal complexes. So that's a problem. Whatever theory we use should be able to do this pretty consistently and for anything that we kind of throw at it. Another limitation is that we have structures with multiple bonds, so double or triple bonds. That was kind of funny, actually. We have structures that have double or triple bonds, and those electrons are able to move more freely than what we would predict using this VSEPR theory. So those limitations tell us, just like with the Bohr model, it's not exactly correct. But it does a good job for most substances, so that's why we teach it, that's why we use it. Because using this table, I think some of you have kind of figured out how to use the table to your advantage. It really is a useful tool in helping us figure out what those geometries are. And as we continue to work with it, it'll get easier, I promise. Okay? So, really what this hybridization theory is all about is how the orbitals merge together and change each other. And all we're doing is we're kind of putting them into a blender and mixing them all up. And did you see the electron configurations? The orbital notation? I'm glad we did that quantum unit early. Right? I can see you're all dazzled. It's alright, it's hidden by your mask. It's fine. So, sigma bonds, just like we've talked about before. Sigma bonds are the physical overlap of orbitals. But now when we talk about hybridization, those sigma bonds are the overlap, and they don't just overlap. They overlap and they change each other. Okay? That's the tricky part. So it is the physical overlap of orbitals. But I have here, I gotta find my mouse. I have here a picture of, this is ethane molecule. You have 2 carbons right here. This represents the carbon-carbon sigma bond. Can you see how those orbitals are overlapping? And then you have the carbon-hydrogen. We have 6 of those sigma bonds. So in this molecule, we have a total of 7 sigma bonds. Anytime it's a single bond, it's going to be a sigma bond. It is the physical overlap of those orbitals. All right? Which could be important later on when we talk about more complex molecules and counting up sigma bonds and pi bonds and that sort of thing. Now, pi bonds, it is the side-by-side overlap of p orbitals. Side-by-side overlap of p orbitals. And they have to be in the correct orientation, so they have to line up with each other. Be up and down, or you can be in and out of the board, but they have to line up. You can't have an overlap when they're in 2 different orientations. Does that make sense to you? Okay. So multiple bonds consist of a sigma bond that has to form first. The overlap has to happen first. And then you can have 1 or more pi bonds form. So in a double bond, we have a sigma bond and a pi bond. That's where the 2 bonds come from. One is a sigma, one is a pi. And in a triple bond, we can have 1 sigma bond and 2 pi bonds. But the sigma bond has to form first. And then the p orbitals have to be in the proper orientation before a pi bond can form. And that is maybe shown here. Okay? It's shown here. And now what this is showing us is in this molecule, this is ethene. This is 2 carbons that have 2 hydrogens each. Those are sigma bonds. And here's the sigma bonds. They have p orbitals that are sticking straight up and down. And see how they line up with each other? They will merge together. That's 1 p orbital. Will merge together to form that pi bond. A pi bond has 2 lobes. So I don't want you to think that that's a triple bond. That's not a triple bond. That is 1 set of p orbitals that have merged together. And that forms the pi bond. So a pi bond has 2 lobes. If this was a triple bond, we would have 4 lobes, right? 1 for each bond. Wrong way. To this?
Yeah.
Oh, don't worry about that. Don't worry about it. Okay. You're fine. Just skip it. Pretend it's not there. Ignore it. Okay. Are we ready? Because that's just orbitals and bonding. Let's get into hybridization. The good stuff, the meat. Right? We've had the salad and the soup. Now we're ready for the meat, the entree. Where's the excitement? Okay. I mean, you can write down the words, but it doesn't mean anything unless you know what they mean. Right? Hybrid orbitals. Wave functions. Wave functions are used to describe orbitals, right? That's what Schrodinger derived. He derived wave functions and the solutions to those wave functions are the region of space where electrons are 90% likely to be found. So that's what a wave function is. Wave, it's just an equation.
Used to describe orbitals.
Yep, used to describe orbitals. These wave functions combine with each other, just like the orbitals combine with each other. We basically put the wave functions into a blender, push puree, and hope something fun pops out. So wave functions, they combine to produce new mathematical descriptions that have different shapes. Do you remember when we talked about the shapes of the orbitals? And we have s orbitals that are spherical. We have p orbitals that are dumbbells. We have d orbitals that are mostly double dumbbells, and then we've got that one weird dumbbell with a donut. Remember those?
Don't remember the donut one.
Yeah, well, that's a weird one anyway. Those orbitals, the shapes of those orbitals are the solutions to these wave functions. Now, I'm not going to get into what the wave functions are. That's way, way, way beyond the scope of this class. And mathematically, they are just equations that describe three-dimensional regions of space, volumes of space. But if we take these wave functions and we allow them to combine with each other, we get new things that describe different shapes. And those new shapes are the combinations of those original orbitals. That's what these hybridizations are. We're basically taking the orbitals that we've been talking about pretty much all year so far, and we mix them together in the blender, and out pops these things that all look the same. They depend on what we put in the blender, but aside from that, the number of orbitals we get out is the same as the number of orbitals we put in, and their shape is described by the orbitals that we put in the blender. That's all this is. I know that sounds not so bad, okay? And you're going to see hybridization is a lot easier than a lot of other things to identify the hybridization. Yes?
Do you say what wave functions are again?
Wave functions are just equations that describe the shape of the orbitals.
So we're just taking the orbitals and we've been talking about combining them to create new.
Yep. Yep. All right, are you ready? Do not try to draw these, because it's not going to work out well. They're all going to look the same, I promise. So don't try to draw these, but I want to show you what they look like. Ready? That was anticlimactic, right? Because I didn't. Okay. There we go. Oh, damn. Where'd it go? Going the wrong way again. I got excited. There. I got excited, and then that was just ridiculous. These are all the possible hybridizations that we have. Okay, not all. SP is missing. Oh, no, there it is. It's the first one. SP. Do you see that where it's got two lobes? It's got two lobes because it's made up of an S and one P. See how we put an S orbital in and one P orbital in? We put two orbitals in, we get two orbitals out. And if we put in an S and a P, then what we get out is SP. Does that make sense? For SP2, that's this one up here. For SP2, we put in an S, and you guessed it, two P's. So we put in three orbitals, and how many do we get out? 3. How's this not knocking your socks off, people? Okay? SP3, we put in one S orbital, we put in 3 P orbitals, and we get out 4. Look at that. Look at these exponents. We got a 1 and a 1. 1 plus 1 is 2, and how many do we get out? That's crazy. 1 plus 2 is 3, and how many do we get out? What? Okay. SP3D. Stupid d orbitals. Remember all those things after aluminum? What's special about this stuff after aluminum? They can have more than 8. And how can they possibly have more than 8? It's the d orbitals. Those d orbitals can hybridize with the s and p. And when they do that, if we put in one s, we put in 3 p, and we put in a D, now we can form 5 bonds. And what's the most number of bonds that we've seen? 6, right? Sulfur can form 6 bonds. It actually likes to form 6 bonds. So sulfur will be sp3d2 hybridized. It puts in an S, 3 p orbitals, 2 d orbitals, and blends it all up, and out pops 6 sp3d2 orbitals. Are we awake? We got the whole gamut of responses there. Okay, so who cares? What does this look like? Looks like a dumbbell. What geometry does it take on? Linear. Do you see that? These lobes are where the electrons are going to be. That means they've got to get as far away from each other as they possibly can. If we have 2 lobes, the farthest they can possibly get away from each other, 180 degrees. That's a line, that's a straight angle. Up here, we have 3 lobes. What geometry does that look like? Trigonal,
Pyramid.
planar. Trigonal planar, these are all in one plane. The farthest they are away from each other is 120 degrees. Down here we have tetrahedral, trigonal bipyramidal, octahedral. Please take out your tables. That look like this. If this doesn't get you excited, I don't know what's going to. Hope that's good news. Nope, not good news. Okay. Not bad news, just not the good news I've seen. All right, so what kind of hybridization do we have for the electron pair geometry of linear? Which one of these looks like a line? So in that far right column, what's the top of that column tell you? You probably should write SP bilinear. 2 electron-rich regions. 2 electron-rich regions. SP hybridization. What about 3 electron-rich regions? SP2. So what's the electron pair geometry for that? Trigonal planar. Trigonal planar. So that's sp2 hybridized. The central atom, sp2 hybridized. What about 4 electron-rich regions? sp3. Right, we have 4 lobes, 4 regions. Are we seeing the connection? Okay, is it losing something on translation? Okay. 4 electron-rich regions, sp3 hybridized, that's tetrahedral. 5 electron-rich regions, that's trigonal bipyramidal, sp3d. And 6 electron-rich regions is octahedral, and that is sp3d2. Do you see the square here in the middle? And then the 2 up and down? Can you kind of see that 3-dimensional octahedral shape? Yeah. Isn't it weird how when you're looking, you know, like when you've first been shown just with those models, like, oh my gosh, now I see it? No weird? No? Okay. I'm good, whatever. Now, in the video, do you remember that he said that lone pairs are in hybrid orbitals? Do you remember that? That's very important. Very important. What else did he say? Yeah, they are in hybrid orbitals. I want to say this because I'm not sure if he came out and said it directly. Hybrid orbitals only form for bonding. Hybrid orbitals only form for bonding. So if we just have a plain old sulfur atom, it's not going to do this. It's going to do what we would predict with its electron configuration. But when we put it in a situation where it's starting to form bonds, it does this automatically. All right? So this only happens when the thing is bonding, when the substance is bonding. It doesn't just happen when it's just plain old an atom of that element. It has to be bonding in order for this to happen. All right, so let's do some examples. I want you to draw the Lewis structures for these two molecules, carbon dioxide and sulfur tetrafluoride. Draw the Lewis structures for these two molecules. I just told my physics class that any of those students, they should come in during one of my chemistry classes or my chemistry 2 class, because I told them that if they don't have if they don't have like 16 pages out doing their work, studying for whatever, or for working through problems, they're not doing it right. So I look around and you guys are like, got stuff everywhere. I like it. Makes me feel good. Draw the Lewis structures for those two molecules. Okay? Oops. Bless you. I mean, I feel like we can modify it. And this, I feel like it's drained.
A grate for it. I only have 32.
Later, alone. Okay, so for the purposes of time, You don't listen.
Wait, look at it?
Later.
Oh.
So, carbon dioxide. I'm gonna go ahead and put this up here. I can assure you that the formal charge is 0 for everything up there. A double bonded oxygen always has a formal charge of 0. And carbon, 4 minus 0 minus 4 gives us 0. So, anyway. I want to show you how we identify the hybridization from a Lewis structure. That's going to be an important skill for you. Hint, hint. Wink, wink. Nod, nod. Got it? Okay. So here's what we do. Because remember, we're going to take all these orbitals and we're going to put them in the blender. And we're going to mix them all up. I want to point out that carbon here is forming 2 pi bonds, one with each oxygen. And when pi bonds form, those p orbitals do not hybridize. We are only identifying the hybridization for the central atom. All right? So what we do is we kind of count our electron-rich regions. How many electron-rich regions does carbon have around it? 2 electron-rich regions. 1, 2. Which type of hybridization has 2 lobes? This is sp hybridized. That was terrible. sp hybridized.
Is that it?
That's it.
That's it. The complete.
That's it.
Then why was it in the middle?
Only the central atom. What do you think? Okay. Sulfur tetrafluoride. Tell me what this looks like. How many total electrons should there be?
34.
I think sulfur should have a parallel.
28 plus 6 is 34. And we've got 28 28 plus 6 34. We have 30, oh, I'm sorry, 32, yes. We have 32 up here now because we've got 8 around each fluorine. I'm sorry, you're right. How many does that leave us?
2.
Where do they go? Has to go on sulfur. No. Fluorine has full valence shells. Fluorine cannot have more than 8. It's before aluminum. It cannot. It does not have d orbitals available for electrons. Only sulfur does. Only sulfur does. So, in this case, those 2 lone electrons have to go on the sulfur. They have to. There's no other way to do this. All right? If you have something if you need to put more dots up there, and you have an element that can have an expanded octet, that's where those dots go. On that element that can have an expanded octet. You do not have to put them as a bond on between anything. They are lone electrons there. So fluorine, formal charge, 7 minus 6 minus 1. Formal charge is 0. Sulfur, 6 minus 2 minus 4. 0. Formal charge is 0 for everything. The hybridization of our central element. Okay? So now, we're going to count all of these. 1, 2, 3, 4. Do we count the lone pair?
Yes.
Yes. A lone pair goes in a hybrid orbital. So 1, 2, 3, 4, 5. What hybridization is this? S, P, 3, D. My exponents have to add to the total number of electron-rich regions. I'm going to say it one more time. My exponents have to add to the total number of electron-rich regions. So we have 5 electron-rich regions. Even though we don't write the exponents up there, if you did, it would not be incorrect necessarily. So if you want to put the ones up there, you can. There's 1 s orbital, 3 p orbitals, 5 d orbitals, 7 f orbitals. Do you remember that? So we've got 1 from the s, all 3 p orbitals. That gives us 4, and we need 1 more. So we have to add in the d. Do you see that? Come here.
So it's just as many pairs.
All the electron-rich regions. So it could be a bonding pair, or it could be a set of bonds. It could be lone pairs.
So it could be anything that's around your single atom,
Yes, unless it is a double bond,
which is two.
which counts as 1 region.
Okay, so
A triple bond counts as 1 region. How are we feeling about that?
so it's basically however many sides on it has.
I feel like hey, but not confident.
Are you asking for practice?
No.
Yeah.
Not today.
I'm not.
Whatever. Who was not in here yesterday? So look at that. We talked about hybridization today. So now you can answer number 4. Yesterday you could only answer 1, 2, 3, and 5. Today you can answer number 4, 6. Okay, that's it. But you can add 4 and 6 to that list now, right? You just have to be able to draw a Lewis structure, calculate formal charges, identify electron pair geometries and molecular geometries, and now identify the hybridization of the central atom. And tomorrow, what time is this class over? I don't have time today. Tomorrow, I'm going to have, oh, this is going to be fun. Are you ready? I'm going to have a molecule that I want you to identify the hybridization of each atom in the molecule. That was a very fun activity last year that we did. So I'm going to have you do that. I'm also going to have you identify the number of sigma bonds and pi bonds that are present in that molecule. That's going to be a good one. All right? So I know you're all excited about it now. Try to sleep tonight so that you're ready for it tomorrow. I'm glad you listened this time. Okay.